So let's look at this final problem right here. Now, in this example, we have the motion of a charged particle in uniform electric field. And as I said, when we solve this type of problem, we're just going to completely neglect. So for now, we just assume that gravity is not contributing anything. Because if you look at this, so if you really want to be correct, you should say that the gravity is going to be acting like this. And then you have some electric force acting like that. But we're saying that because this electric force is way bigger than this force of gravity, we can just forget about the force of gravity and the focus of this electric force that is acting in the system. All right. So now, this is the problem. The problem that we're trying to solve is this. Suppose that, now let me open a new. So suppose that I have a let's see. Now this can be done very easy in real life. So in real life, basically what you do is that you just connect a power supply here. This is a battery. You connect a battery such that the positive terminal is connected to this plate here. So this would be a positive charge. This would be positive charges here, and this would be negative charges right there. So when you do this, you end up creating a uniform electric field in between this region here. And then we're going to say that let the distance between this point and this point be equal to B. Then I have a proton. I was coming in with some initial velocity VI. Can I calculate the X, the final velocity when it exits? So in between these two plates, there is an electric field. And we're going to say that this electric field is uniform and has a value of, let's just say 3.0 times 10 to the power 6 per coulomb, pointing in the I-hat direction. And let's suppose that the distance between those two plates is equal to 1.0 centimeters, which is 1.0 times 10 to the negative 2 meters. Now suppose that we have a proton that was moving with some initial velocity that was equal to 2.3, 2.6 times 10 to the power 4 meters per second. What is the final velocity if the distance between the two plates is given by that value right there? So if you look at this problem very well, so you have a proton. We know what the charge of a proton is. So let me write. So the charge of the proton is equal to 1.6 times 10 to the negative 19. Now let's think about it. If there was no electric field, this is just going to keep moving on a straight line with the same velocity, right? But the presence of the electric field is going to accelerate the proton. So I want to calculate what this final velocity is. So what's the best way to solve this problem? To solve this problem, I can say that I'll write this equation down. So let me write this equation down and then let's see if we can use, so V final squared is equal to V initial squared was 2 acceleration, x final minus x initial. Now look at this equation and kind of tell me if we can use this equation or not. So do I know what my V initial is? It's 2.6 times 10 to the negative 5. Do I know X initial? I can set that to 0. Do I know X final? I can set that to the distance, which is 1.0 centimeters, which is my 1.0 times 10 to the negative 2. So all what I need is to get my acceleration, right? How do I calculate acceleration if I know electric field? If I know electric field and I know the charge of the test particle, multiply Q by electric field, it gives me force. Divide force by mass, you get acceleration, right? So the only thing that we need in this equation is to figure out what the acceleration is. And I can get my acceleration pretty easily from this equation. So acceleration is my test charge times electric field divided by mass. This equation right there. So once I get this value, I plug that in here and calculate my phi. So let's plug in the numbers here. Let me look at my calculator right here. So if I do my math correctly, so let's plug in the value for the mass of the proton, which is 1.67 times 10 to the negative 27 kilograms. So if you plug in that value, you get your acceleration, which is equals to, so this would just be equals to 1.67. Multiply this by the electric field, which is 3, divided by the 1.6 times 3. So this should give you 2.87 times 10 to the power of this is what I got here. This would be 8 meters per second squared. Then if you take that value and plug it in, right, so you know what the acceleration is, you can plug that into that final equation. So if you guys can kind of complete this problem. Now let me show you, so we have about 8 more minutes. Let me show you one more problem here, and then we'll probably just pick it up from next week. Now let's look at this example here. Suppose that I can put, so let's have, so this is a region where we have, so again, this is positive here. And this is negative. We have an electric field that is pointing out like that. The problem tells me that the electric field again is uniform. That's a 3.0 times 10 to the power 6. This time around it's pointing in the J direction. Now I'm going to go ahead and add, so let's say that this line is my x-axis, it's my I direction. And this is my J direction. Now, I'm going to take a small particle here. This is a proton. I will give it some initial velocity, and that initial velocity is VI. It's equals to, let's say, 2.6. Now, again, let's just forget about gravity. So how is this particle going to move? Is it going to keep moving on a straight line?
No.
Does it move up or down?
It'll move to the right and up.
So it goes something like that. You guys see that? So do you see that this is exactly the same problem as the projectile problem? And so what I want to calculate is that I want to calculate this final displacement. So that we know what this distance is here is d. So by how much does the particle? Now, I'm going to show you next class that in this problem here, we need acceleration in the x direction. We need acceleration in the y direction as well. What do you think is going to be my acceleration in the x direction? It's just 0. Because the electric field is only pointing in the y direction, right? My acceleration in the y direction is going to be my charge Q naught times E divided by mass. Now, if I know acceleration in the x direction, I know acceleration in the y direction, I can go ahead and write my equation. So all the equations in the x direction will be something like Vx is equals to Vxi plus Axt. And then you have x final is equals to x initial plus Vx initial times t plus 1/2 Vxt squared. So those are the motion equations in the x direction. Then I can also write motion equations in the y direction. So Vy is equals to Vy initial plus Ay plus t. And then something like, let's say, y final is equals to y initial plus Vy initial times t plus 1/2 Vy times t squared. I've gone over this very quick, but I think next class we're going to sit down very carefully and try to solve this problem. But the only difference here is that we need to look at the x. So there is acceleration. In the x direction has no acceleration. I only have my acceleration pointing up. So when I solve this problem here, I need to apply the x equations and the y equations. So let's see. In the next class, this is what we're going to do. We're going to look at this problem here. So we'll solve this problem, and then this is the one that I'm talking about right now. So basically, we'll solve this problem right there. Right? So in this case, it's an electron. An electron carries the negative charge. So you can see that if there was no electric field, this electron will keep moving like that, but the electric field is going to cause this electron to move down because the force is going to be negative 1.60 times 10 to the negative 19. Then you multiply that by the electric field, which in this case is equal to 200. This is pointing out. So the force is negative, it's less than 0.